In this section, I'd like to briefly consider the role of the cerebellum in speech processing. The primary path for behaviors of releasing cortical activity from one area to another is from the cortex through the basal ganglia to the thalamus and back to the cortex. But the route through the cerebellum targets the same parts of the thalamus as the basal ganglia, so outputs from the cerebellum can also trigger release behaviors. Let's think about what's going on in terms of this rather more extensive cortical architecture. In this architecture, there are areas detecting receptive fields within current auditory and visual inputs, and areas detecting receptive fields defining combinations of receptive fields in other areas that have been active in the past at similar times. Some of the behaviors involved in speech processing are releases between auditory areas at different levels of complexity. Other behaviors are releases of activity in an auditory area to an area that detects that groups of auditory columns are active that have often been active at the same time in the past. And yet other behaviors are releases of those often active in the past at the same time receptive fields to visual areas to drive indirect activations. If the activity, say, in a visual area needs to be prolonged, that prolongation behavior involves release of the visual activity to an area that defines and detects very short-term receptive fields, and release of detections from that area back to the visual area on a loop, as we discussed under working memory. Then there have to be releases at the right time between visual areas on different levels of receptive field complexity. So speech processing is made up of long sequences of these different release behaviors, and some sequences will be used repeatedly in the same order. When sequences are being learned, the basal ganglia will select the next behavior in the sequence and trigger the thalamus to implement the behavior. But once it's learned, different cerebellar nucleus neurons in one microzone can target the same places in the thalamus as the basal outputs at different points in the sequence. Purkinje neurons have receptive fields made up of whatever cortical receptive field combinations happen to be active at just the right moment to trigger the release. And inferior olive neurons tune the Purkinje fields to get the timing exactly right. So, as for other motor and cognitive processes, cerebellar microzones can be programmed to drive the appropriate sequences of cortical release behaviors to support speech processing.